So first of all, I would like to thank Professor Academician Jakvilo for inviting me here. It's an honor to address this audience. And yes, I will be talking today about artificial intelligence-based analysis of drawing and writing tests for Parkinson disease diagnostics. Well, I will structure my talk around maybe three main points. So first of all, I would like to address the elephant in the room, and I would like to explain what I think artificial intelligence is, because there are quite many researchers, there are quite many practitioners dealing with AI, and in many cases it sparks some conflicts because people do not speak the same language. So we should explicitly agree and be on the same page about what AI is. And most probably also I had some kind of interesting experiences working not only for academia but for private sector, for industry, where I saw quite not only successes, I saw quite many failures. So I will try to also address what on my viewpoint was the main point of failure. And then I would like to speak about this area of application, about basically how medical doctors, how practitioners assess and how they use drawing and writing tests to assess or diagnose Parkinson's disease, assess its severity. And then I would like to give or point out some challenges, and most probably challenges, it would not be just a single point, a single part of my presentation, but challenges, I will outline them when we will approach them through, let's say, timeline or workflow of how I use AI. So let's proceed. But first I would like to say that some results which I will present, it's not just only my result, it was accumulated during more than 10 years of research together with my colleagues from Tallinn University of Technology, from Tartu University, from Tallinn University, and even from some of my colleagues abroad and from hospitals in Estonia. As you can see, it's quite many people, and to name all of them now would take quite a lot of time, but I hope I did not forget anybody. I think that giving credit to everyone is very important. Okay, so what my understanding of artificial intelligence is, I think really that if we look back, we can say that Dartmouth conference back in 1956 was kind of point when approximately 20 scientists, they map initially what artificial intelligence is. And those time in this conference or workshop, there were not only mathematicians, computer scientists or computer engineers, there were economists, psychologists, etc. So from the beginning, the area and the field of artificial intelligence was not only directed towards computers, to be part of computer science. And also, when it's all started, expectations were very high, but technology and methodology was not yet sufficiently mature to meet these expectations, which caused a number of so-called winters of AI, when interest towards this technology, towards this area of science was kind of low. But governments were always aware about this, and maybe it was not on the front pages, but investment were made. And how many of these winters of artificial intelligence took place, we can leave this question behind the frameworks of my presentation. Some suggest one, some suggest three, but this has happened. So if we go from historic perspective to something more concrete, what actually forms this AI, and how AI relates to a similar or neighboring disciplines like data mining, machine learning, etc. So initially we can start with data mining. With data mining, again, as a discipline or as a field which identifies 4 so-called super problems to solve. The first of them is unsupervised learning, when you're given a data set and the goal is to discover internal structure of this set. So basically to divide it into subsets with respect to certain criteria, certain features, etc. Then we have a supervised learning, and supervised learning assumes that we do have labeled data sets. So basically this structure is given, but we need to create a machine or an algorithm which will learn this structure, and when based on this structure will classify previously unseen element. The fourth problem is anomalies or outliers, the analysis, the detection. And here what we do have here is that we do not have any labels, but we assume that we have some sort of understanding of what normal is, and we would like to find something which is not normal. And finally, which states maybe slightly different with respect to methods and everything, is association patterns. So here the idea is to analyze finite discrete sequences and find most common sequences, and for example, if you're given a part of sequence, to guess what will be the most likely continuation or missing elements of this sequence. Well, this all is very interesting, but the question is, could we tackle these problems only from a data perspective without any machinery? Because even if we bring a simple metric function on board, it immediately becomes a machinery. But still, data mining exists as a separate discipline. Then we go to another side of the story, how to solve all these problems. And solving these problems requires to combine mathematics, probability statistics, etc. And so basically we take quite a lot of ideas from computer science and merge them together. And then we get a machine learning perspective. So machine learning concerns with algorithms, how to solve all these problems. And of course, when we deal with these problems, machine learners, they brought their own perspectives. They start to talk about semi-supervised learning, self-supervised learning, etc. So it's more algorithmic perspective. But it's still more science than something which can give us some output to be used outside of scientific lab. And here we talk about data science perspective. So here we bring on board context, area of application, infrastructure which we have, resources, limitations, some for example law or ethics norms. After all, our users are maybe humans, and this also brings some constraint. And in many cases, when we all this pack together, a result may be considered to be artificial intelligence system or system which is based on artificial intelligence. I know that this diagram which I present here, it misses one very important part, and it may anger some researchers who work mostly in the part of reasoning, in the part of logics, automatas, because this also may belong to the area of artificial intelligence, but it's not presented here. Basically, I incorporated here in the part of computer science, because most probably, well, a little bit egoistic perspective, because myself I am more dealing with the statistical machine learning. So we're taking from mathematics, we take a formal language and some tools, probability theory and statistics. Well, it's methods also, and it's paradigm, because our data usually probabilistic by its nature. And then computer science give us algorithms, logics, and stuff like this. Well, proceeding to this, so how this diagram, which basically explains my view on what is AI, how it's related to data mining, data science, and machine learning, how it's usually results in something more solid which should work. So, and here maybe one of the most important point is a workflow. And of course, this is my view on the workflow, how I tailor it for myself during many years of working in this area. So first of all, we have two very important components. It's process or phenomenon which we study, and during this process of phenomenon, we assume that some information may be gathered or it's given or something like this. And then the second, there should be a solid problem statement, and this solid problem statement is not different from any problem statement which you state for any other project or application or activity. Maybe for example, starting your PhD research, you also should have problem statement and develop it into more detailed form. Because without solid goals, it's becomes something like very strange activity. And then we start first, so we have our process of phenomenon, and we assume that either someone or we have access to it, so we can gather data. So the first step is to gather data, and by the way, nowadays it sounds quite funny. In many cases, representative of business, of private business or industry, they may address us to help them to use artificial intelligence, but they miss two key components. They miss formal problem statement, what they would like to get. They heard the word artificial intelligence, it should be everywhere now for their perspective, but they do not know what they want. But even if they have a solid problem, we ask, do you have data, or could we gather the data? And this is usually one of the major points of failure. It's a point where, in many cases, project stops and doesn't go further away because they don't think about it, or the data is unavailable, or data is classified, or they do not want to share it, etc. So they do not agree to include into their workflow the part which will address the social, ethical, and lawful components. For example, if you work in the area of medicine, you need permission of ethics committee, which is not that easy to get. And for example, for me, it took 2 months of my time to get proper permits. So once we have a data, it may be the case that we will be able to reacquire the data if we will find out that we do not have it. Maybe not, but then we go to data preparation, feature engineering, selection, choosing hyperparameters, etc. This itself, in my diagram, this is a big part, and I did not split it into the different parts. Most probably everyone should do this for themselves, because your work may be obviously be different from my work. Within this big arrow, there is quite many small sub-steps, but I do not want really today to go into technical details and address some smaller parts like feature selection, or for example embedding feature selection into nested cross-validation loops, etc. Maybe each of these points requires separate lecture. But what happens is that if this part is done, you usually end up with a data which is sufficiently good in order to train and validate the algorithms which we use. Be these machine learning, statistical machine learning algorithms, simple algorithms like decision trees or support vector machines or XGBoost, or it be more complex algorithms referred to the area of deep learning, like convolutional neural networks, or something even more complex. So once we're satisfied with this part, we go to testing, where we test in some other maybe data sets, or test already in the field, for example, trying to deploy our algorithms and give these algorithms to practitioners or to those who will work with them. And then nowadays, after getting this model, which we are happy to deliver, nowadays in many areas there is another very important step, which is called explanation or interpretation. In many areas it's becoming mandatory because, for example, in the areas of finance, in the area of law, in the area of medicine, you should be able to explain why certain decision, when certain classification decision was made. So for example, why we think that given individual or given subject has a Parkinson disease, or for example, why we think that this is not Parkinson disease, but this may be Alzheimer or something else. And then, so I will touch this part in the end of my talk. And then there are two more parts which frequently overlooked again. Is the reporting? Well, this may be less overlooked because someone have to write a report if this was a grant, or if this is not a grant, but if this is private contract, someone should provide documentation and everything. And then there is a model deployment, which for scientists frequently is out of the scope of their research. Here you need a trained specialists who can able to deploy it and maybe even provide support after it. So why I think that this workflow is very important, because in many cases when even all the prerequisites to problem statement, to having the process, securing the data, permissions and everything are satisfied, in many cases companies or researchers, they fail to position properly this workflow in their research, in their activities. So for example, if you are building AI startup, this should be in the core component of your work. If you do not want to become AI startup, if you, for example, work in the area of chemistry, medicine, or whatever, you should still somehow separate and create a separate entity within your organization where you put this workflow and you build your activities around it. This, in many cases, will assure your success. Okay, this is workflow. So how we used it in the area of Parkinson disease diagnostics. But first, I would like to make a short step back and explain why I'm doing this human motion analysis. So basically, after I defended my PhD, it was about nonlinear control systems. I decided that I need something new, and it was an interesting project. It was not my project, with where Japanese university, Tokyo Denki University, was involved. And what they wanted to do, they wanted to create a scrub nurse robot. Scrub nurse is a nurse which assists directly to operating surgeon. Why they wanted to do it? For a very simple reason, because in Japan they have, in spite of the fact that it's a popular country with a high population, they face a problem. They do not have enough scrub nurses. And they also have certain cultural problems, like operating surgeons do not talk too much. So what we needed a machine which will recognize what operating surgeon is doing. So by analyzing their hand movements, not gestures, movements, it was necessary to predict a part of the surgery which is taking place and decide if assisting action is required or not. But then they had earthquake in Japan, and then some of my colleagues there, they defended their PhDs, went for postdoc, etc. So I started to search for contacts in Estonia. And first we worked with rehabilitation doctors, so post-stroke, post-traumatic rehabilitation. Also developing similar things. So basically we wanted to create a machine which will supervise physical exercises. And later somehow I find the contacts first in Tallinn University and then here in Tartu University Hospital, neurology clinic, where they were interested to listen to us, and they had also problems to basically not supervise these exercises, but to use these machines to detect. And we started with analyzing gross motor movements, but later we find out that concentrating our attention on fine motor may be even more interesting, because when you're given a piece of paper, or instead of paper you're given an iPad or some other tablet PC device, you are much more limited in what you can do, and in this sense we get much cleaner data. So we decided at a certain point, taking into account also our resources available, because we do not have too many students to give, or too many researchers to deal with each particular case. So we decided that most probably we would like to concentrate on this part. So what is Parkinson's disease? Well, I'm not a medical doctor, but what I know and what is important for us. First of all, no cure is available for it, unfortunately. And I work in this area for more than 10 years, and each month we hear that cure will be ready by next month, and still it's not here. Then symptoms, they affect the quality of everyday life. This is very important, because Parkinson's disease was not necessarily may shorten the lifespan. It definitely can do it, but it makes someone's life rather miserable, because of there will be some rigidity in motions, freezings, unpurposeful motions, etc. Then we talk about subjective component in diagnosing the disease. While working with our colleagues here, we observe that younger, less experienced practitioners tend to underestimate severity of the disease. So I already mentioned that basically the particular area is chosen because we have here people who are willing to cooperate and to work with us. And then there is a monetary factor. There is a time frame which practitioner allowed to spend on to examine Parkinson's disease patient. I can't remember, 1.5 years or 4 months, but this time frame was 20 minutes. It's very short to deal with people who may have problems with speech, who have problems with walking, and you know that here in Estonia, but not here only here, in many developed countries, medical system is overloaded. So our idea is to provide some tool. We do not want to replace medical doctor. I think that it's not a good idea, but we would like to provide a tool which will basically support them. And our formal problem may be split into two parts. The first is diagnostics. We would like to have a machine which will diagnose Parkinson's disease based on writing and drawing tests. I will explain what these tests in a minute. And also here is a second part which we would like, which we have a scientific component, because nowadays having all our tools which may register pressure, accelerations, compute the derivatives, etc., we can see more than naked eye can see. So here is also scientific component, what we can discover about this disease. So what is our background knowledge which we used in order to basically implement all the parts of the workflow which identified before? The first part, the question is how we move. The first is decision. For example, I'm hungry and I am decided to walk to fridge, assuming that there is a food, so I would like to take it. But this part, decision, we're not touching. So, and then once decision is made, we have two phases in our activities. The first is a planning phase. What happens, your brain generates a sequence of impulses which will be sent to spinal cord. And then execution, when the sequences are sent to spinal cord and spinal cord start to control muscles, contractions, and then you basically walk or do whatever you decided to do. The problem is that Parkinson's disease affects the both sequences. Sometimes one of them, sometimes both. So in planning phase, what happens? The sequence of impulses, it's called motion melody, and it becomes not optimal. So basically, if we consider the process when child was born and started to walk, so basically in the early stages of life, so if you take these early stages of life, what child is doing, child is learning how to move all the aspects, how not only how to walk, but how to plan the emotions. And what happened if you have a certain scale of optimality during the first years of activities, what happens? The child improves the ability to plan their movements, and also they improve the ability to execute these movements. And even not only child, for example, when adults, if I will start to play tennis, in the first I will take this racket and I will be very clumsy person, but well, if I'm still physically okay, then after a certain period of time my motions will become smooth, my planning will become good, and most probably I will reach some good level. Of course I would not become a world champion anymore, but anyway, so no big slam tournaments, but most probably just playing tennis for fun I still can do. For example, to mimic this, when we still was working in a gross motor area, we took a very simple test, basket, and we created a balls, but not ordinary balls, because ordinary balls, you all know, we take a paper, we jam it. So it's not, these balls were not very good, and when we record trajectories of the hand throwing them, and it was very interesting to observe that in approximately 10 to 20 sessions, trajectories start to follow for each person one and the same path very, very closely. So this is what happens in the early years. Well, then we enjoy some part of life, and then unfortunately we start to age. Aging also start to affect all this planning and execution phase, but if you exercise, if you basically do your homework properly, most probably you can slow down this process. But traumas, neurologic diseases and stuff like this, they affect these sequences, and then somehow they started to become less optimal. They started to decline. And this is what we would like to catch, what we would like to detect, and what we would like to assess. So what are the symptoms? More specifically, if we take any medical book, you will find out that there is a rigidity, freezing, non-purposeful motions, and tremor. This is what our colleagues distinguish. And what does it mean, rigidity in motion? It means a greater effort to overcome it. So motions are not smooth, and it's reflected by accelerations. So we have something related to acceleration. The same goes for freezing. Freezing itself may be detected, and by the way, it may be cause of a patient will be falling, but if not, then again we have problems that most probably accelerations should be higher to overcome it. Then we have non-purposeful motions. So what does it mean? It means that our motion melody, our program to deal should be adjusted, and again this we will have longer trajectories. And then when we talk about motions not smooth, again this is tremor. Tremor itself also may be detected with more formal tools, but again, it's accelerations. So we can continue this, but these are the most important symptoms, and therapies exist. In many cases, this is just a physical therapy, physical exercises, which allow someone to overcome this problem and live sufficiently healthy life. When I once attended the conference, our Estonian Conference of Neurologists, they show a video how patients were transported to the hospital, and this patient was not able to walk, but after 2 weeks, the patient was able to run down the stairs. So it's quite a good progress. So, what our experimental setting here? I would like again to remind that when we talk about motor activities, we have gross motor level, where we address limb movements during walking, sitting down, standing up, etc. But this is another part. We achieve certain progress, but then we switch to this fine motor. And in fine motor, we also distinguish two parts. One is drawing and writing tests. I will be talking remaining part of my lecture, and the second part are activities which requiring to grab and place small pieces of objects with fingers. So usually patients are given such a plate with small holes where small object positions, and then they ask to take one and position to another place. So let's talk about drawing and writing tests. First of all, it's very many of them. Most popular test is a spiral drawing test or Archimedean spiral drawing test, and our medical colleagues, they ask us to put word digital in front of it, because nowadays what we do not give patient a paper and pen, we give tablet PC and a stylus. This is what we do. And digital, of course, it brings certain difference component, because some screen may be more slippery. It's not exactly paper and pen. But obviously, the drawing, well, for us it's on the right, is produced by someone with a certain neurologic disorder. Well, here I can say that it was a Parkinson disease patient. But if you will be asked to distinguish between first two spirals here, what do you think? Who of them is healthy person and who of them is not? The right one, yeah, but if you analyze just left and middle. So you think that middle is healthy? No, they're not artificial. They're both patients. It looked more natural, it's true, but the problem is actually the left one person is healthy, and the middle one, unfortunately, this was a Parkinson disease patient. The problem with us here is that among elderly people now, there are many of those who are bookkeepers or some people who had to write all their life. Their motor functions are that good that they are not that much damaged. So basically, we may have false negatives too. But popularity of this Archimedean spiral drawing test also is a course of this test. Why? Because different medical schools assume that this test should be conducted in a different ways. In Estonia, here, patient was given a paper with a reference drawing and asked to draw in one stroke from outside to inside, such that they do not touch the contours of a reference shape. But, for example, in Czech Republic and Slovakia, they ask to follow the contour. In some other countries, they show you the contour, but you should copy it on a white sheet of paper. And this creates this difference. On first view, you still should produce a spiral, but these spirals will be very different. So this is the simplest test, and most probably it was the most played. When I did my literature review a long time ago, I found out that it was implemented even on a first small handheld devices called Palm, some kind of. machine like this. My PhD student, before she defended, she implemented it for iPhone and Android devices. In our case, we also implemented basically for all computers we had in our possession. But it's not only one test. Then we go to another test. This is called Lurie alternating series tests. And Lurie alternating series tests were initially designed in order to capture the problems when someone have to switch between different drawing programs. So you have first test P lambda continue test. So P lambda test, you can see that you have two patterns, capital P and capital lambda, and what you need to do, you need to continue, copy, or trace the test. Continue is clearly oriented towards planning function, and trace is to execution function. So we had two versions, but during the time we converged to have just P lambda continue and P lambda trace test. Here was not the problem that we could not extract any information from other tests, but usually you deal with the people who are whose motoric state and fatigue state may be affected by a longer session needed to conduct all the tests. And here we observe the fact that even healthy individuals, sometimes when they are tired, they have a problem switching between drawing letters P and lambda, which give an interesting perspective for our future research. So initially this test was designed to observe mistakes done by the subjects, and not to analyze kinematics. So here in spiral drawing test it would be obvious to analyze kinematics, but here not. And then there is a sentence writing test. Any Estonian knows that this sentence states that when Arno and his father arrived to school, lessons already started, and it was studied in all schools which were operating in Estonian language, and it was written many times. So most probably if individual has a problem with writing this sentence, then something wrong with their motor functions. But here we started to face now the problem. Younger generation of my bachelor and master students, whom my supervisor told me that in the school we do not study this anymore. And this basically makes a problem. And also another problem that in our lives we do not write that much. So a simple writing task may become challenging for those who only typing something in their chat devices. So keep this in mind. Okay, I can continue obviously talking about different tests, and I will highlight a few more tests during my today presentation, but this is not the point now. So you already, I think, have some understanding of what kind of exercises are given to the tested subjects. So how the data acquisition process occurred, so how we basically get our data. So in a former times, and by the way it still remains some subdirection in this area, doctors were using a sheet of paper and a pencil. And what was very important here is that human observes how patients perform this exercise, and then subjective opinion, usually good training, and you can have understanding if we talk about neurologic disorder or disease or not. So we started with first we started with Android tablets, and then we switched to iPad, and finally we converged to use Microsoft products. And this was purely for technical reasons, because first in the case of Android, these versions pop up very frequently. There are quite many different versions, and it's very difficult to work with their SDK. Then the second part was iPad, everything is noise, but you should pay them to develop software for them. Basically, it's strange. And also, the biggest problem was that what you see on the screen is not what exactly is under the screen. Resolutions of the pen and the resolution of the screen were different. And finally, we find that Microsoft Surface works the best for our purposes, because it's a basic computer which medical doctor can use not only to conduct tests, and it's much more easy to deal with them. And by the way, on the last image, what you see is a Pepel-Reuters test of overlapping figures, where the patient should trace the figure either shown on the screen or named by those who give the test. And again, observing how correctly it's done, some assessment may be made. So what happens on the level of data, where we get the data? So screen of our PC, or before, when if we would like to analyze all the tests, we need to digitize them somehow. So what you have, you can think this, that we have coordinate system. Obviously, coordinates on your iPad or Microsoft Surface, they run different way, like for normal people, but this is a minor problem. So what you have then, depending on the sampling rate, sometimes up to 200 times per second, you can get a location of a stylus tip. And then you can get a pressure of the stylus tip to the screen, what you could not get with the paper. And from this, well, it's a simple mathematics. What you can do, you can compute quite a lot of parameters. You can compute velocities, you can compute accelerations. We went up to six derivative of this in order to see what will happen. Then we computed quite many different angles in order to again observe how smooth was the motion. We obviously applied partially this to with our derivatives to the changes of pressure. So you can imagine that it's quite many parameters. And obviously we did not have that many patients to take into account all the features, and also all the features here are not necessary. But when we proceeded to feature engineering and feature selection, we also brought something on the table of this research. From our part, we suggested a set of integral-like features which describe smoothness and quantity of motion during certain time interval, not just in a particular moment. And we call this motion mass parameters, and they appear to be more informative than many parameters which were used before we joined this research direction. But just to say what else here is available is it's a screen time, so basically time when someone was actually drawing the picture, not just hovering the pen above it. Then there is hovering time itself. Then there is a freezing time, obviously number of freezings. We can continue to many features may be projected to both coordinates x and y. And once I computed just for fun how many features we can construct if we will all join research back approximately 5 or 7 years ago. And it was approximately 2,000 features per test. And obviously we do not need that many. Then here at this point, when we got our features, then we applied this artificial intelligence or machine learning workflow. We applied it straightforward. So basically we applied it, we constructed nested cross-validation loop, and in this, because all features are numeric, we use Fisher score, which basically orders features with respect to their discriminating power. alternative may be to play with entropy, so Gini indexes, but they will give approximately the same at the same time. And what we have achieved in our research group? In our research group, basically, we started, and first, having small data sets, we concentrated our attention on the decision trees, on the support vector machines, XGBoost to find the best, and we achieved the goodness of our models to be between 0.85 and 0.9 for different goodness metrics. But here I have to emphasize that basically what was it? It was goodness of mimicking the human doctor. It's not absolute goodness, because you can get medical doctor also can be wrong, by the way, and also as they said us, that final diagnosis can be confirmed only after the death. We do not have such data sets in my knowledge. But still, 0.85 or 0.9 is quite good. So the question is, could we stop here? Maybe we should not do anything more. But the problem is not exactly solved here. What we demonstrated, it was just a first step. We demonstrated, yes, we can mimic human. These methods are very suitable for the problem, and even we can say that most probably, since we're able, and many others able to publish in higher level journals, these problems are accepted by the community. But what next? Is problem solved or next? Well, I will skip here a small step. We applied here this mechanistic interpretability, because here what you will have a very simple answers. For example, the major factor was tremor, or the major factor was, for example, length of trajectory. But the problem is, what happened? We created a gap here. I do not say that it was just our group. All the researchers which work with machine learning, statistical machine learning, we created a gap. And then I still would like to discuss the problem. We have another test. We have a test where semantic component is more important than kinematic or pressure component. And then finally, I would like to return the question of interpretability. So, where is the gap? What is the gap? The problem is that we created very accurate models, and most probably if we would invest more time, we would somehow get larger data sets. Most probably we can even do it better, but our models, when they're statistical machine learning, they do not take shape into account. And human practitioners, they were taught to observe how drawing process going and see the shape. And here is a question. Would deep learning here be an answer to these worries or not? Can we use deep learning in order to address it? And there is two problems. We have a data scarcity, so we have a very small data set. And why we have these smaller data sets? The largest, what I observed in the literature, was something 400 tests, which is definitely not enough for any serious deep learning application. But usually data sets are below 100 tests. And still, analysis of complex images. So let's talk about what we already have done in the area using deep learning, and let's see if it answers the question or not. So what we can have different representations. And also, my personal dream when I started this work with a few PhD students, my personal dream was, okay, we have a shape, but shape is black and white. It's just a contour. Could I still somehow encode parameters or describing pressure or something else and get more data? So we had one student, and basically what he did, he started with one-dimensional part which gives kind of shortcut also to using models to analyze sequential data like LSTMs. Two-dimensional representation may be the most normal or the most obvious way to proceed, and then there is a three-dimensional representation, because then you can encode quite a lot of data here. You cannot just use, for example, thickness of the line or color. You also can use third dimension, for example, to encode the pressure applied to the pen, and you can use color for something else. And here we compared, in one of our papers, we compared convolutional neural networks for one-dimensional case, for two-dimensional case, and for three-dimensional case. What we got, where we were happy with the results and where not. The first, I will start from the part where we're not happy. We did not get more accurate models than you can get with a statistical machine learning. But where we get very interesting results, we get very interesting feedback about interpretability of these results, because our colleagues in different countries, they said that they like very much this colored representation. Again, 3 dimensions was a little bit difficult to sell, but color was accepted quite well. And now what I can say is that if you will scan the papers about the applications of CNN, convolutional neural networks, for drawing test analysis, most probably this will be the top technique which is used. Quite many publications in high-tier journals address this issue, and I think that this is right, because it's really, even in its simple form, it allows to do quite a lot. Then it's application of long short-term memory models. So what you have here, you obviously can consider the processes to be simply a time series. And then you can try to apply LSTM models in order to get some information about the drawing process. For us, pure LSTM did not work very well. We still combined it with convolutional neural networks, and it worked much better. Kind of lightweight model, which also address our problem and provide very good result. But still, returning to the previous slide, I can say that unfortunately we was not able to go high above 0.91 in terms of precision and recall. And I observed some papers which report maybe more accurate models, but here is a problem: what is your data set? Because in our case, the problem was very strict, because we had 2 groups of individuals. We have PD, like we refer Parkinson disease patients, and healthy control individuals. We managed here in Estonia to find 2 groups of people, to combine 2 groups of people which had approximately the same gender distribution, approximately 50-50, and they were the same age. Of the middle age was something like 69 in both cases, and our standard deviation was approximately 6-7 years. So our groups were very good. In some cases, I observe what is happening, and this is very understandable. Group of Parkinson disease patients is not much different from what we have, because this would be the mean. It would be the mean age for Parkinson disease, let's say 10 years or 12 years ago. But instead of healthy controls, of the same age, you have a group which will be from 18 to 49 of the same size, but with much larger standard deviation and absolutely different mean value. So in this case, it's much more easy to distinguish between two groups. Well, proceeding, what next? Yes. Yes, we assume that our doctors were right. Yes, absolutely.
Which of course is another problem, because they might not be.
Yes, this is a problem, because as I told, basically diagnosis may be confirmed only after death.
I know, yeah.
So here we should observe, obviously I would say that if to plan larger research, it would be interesting to have a sample where, for example, 10 different doctors from preferably different countries made the same diagnosis. Then we can be more...
Okay, that would be one way, because that might also help to have this gap discussion a bit better, because the models might make different mistakes than the humans.
Yes, absolutely.
Good. Yeah, but okay, that's I just...
So another small success which we achieved, we used deep learning tools, and we are using quite a lot in order to extract individual elements of a drawing test. For example, for this P lambda for Luria alternating series tests, it is important to find out different elements of the drawing. For example, is it vertical stroke, horizontal stroke, diagonal stroke? What we observed that actually some parts of the drawing are more informative than the others. So we return here from another part to the question of feature selection. So we're not interested in just take entire test, compute parameters and be happy with it. We're interested to find out which parts are more informative. And for example, in our research, we managed to very precisely to distinguish different components, but we also find out that, for example, starting part of the test, it contains more information than the middle part. I do not say that we should ignore the middle part or exclude it. No, we still need entire test, but starting part will be the first here, and also stopping part, because many Parkinson disease patients, they have a problem in completing the motion. The other part, the second part, where we successfully used deep learning methods, for me was personally scary when my students showed me the results. And why it was scary, so how can I... how can I start them? So here we applied generative adversarial networks in order to augment our data set and create larger number of pictures. So what was scary for me is that especially the spiral on the right, as you can see, it's sometimes not, during its evolution, it's not spiral anymore. It's something different. But what we observed, when we started to use this method, now it's definitely not a spiral. And when we started to use this method, what we observed, obviously, we observed some small boost in quality, but what was mostly important that we achieved sufficient number of samples in our data set to train our deep model, the models without any problems with overfitting, etc. All the graphs were quite nice and quite perfect. But I really was scared when I saw that spiral sometimes turns not into spirals, so machine thinks out some other features of the drawing which are very important to it. And thanks to this method, we basically managed to increase our data set here, and obviously for us would be the next step to augment other data sets which we do have, other tests, in order to be able to basically apply this machinery to other tests. So how, wait a moment, I press something which I should not. No. Okay, so let's summarize where we are now, and then I will give some outline of where we're going, or which direction we're going in the future. So like everyone else, we started with simple statistical methods. We proceeded to statistical machine learning techniques. We went to supervised feature selection and some mechanistic interpretability. Maybe here I should spot some more light when we realized that simple machine learning technique with a feature selection, with everything, works very well. We got the feedback that, okay, our colleagues, they do not want to operate on a 6-order derivatives. Well, we can explain what is it, but we were asked to tune our machines to operate on features which have very clear meaning. And then we basically adjusted the feature set with respect to feedback of our medical colleagues, and then we got very nice models which in some sense may be treated as self-interpretable because they operate on a feature set of 3 to 5 features. And then we tried simple deep learning models. We were happy with the result, but well, here is nothing in the terms of quality. Here you do not have anything which distinguishes them from classical statistical learning. But deep learning as a tool works very well for us. And so what's next? We have analysis of more complex tests, and we need to explain the results before we can obviously jump also into the other areas. So first of all, I will show you 2 tests, and these tests are frequently referred as embedded figure test. What is here? How these tests are working? On a test which looks like a honeycomb, the tested individual is given this picture and then asked to replicate this picture below. So I would challenge you here, do we have anyone who would like to try to do it on a blackboard? After all, here we have real blackboards, not a whiteboard. Do we have any brave person here? Yes? Come here. Yeah, honeycomb. Very good. Fantastic. Thank you. So, well, now I will explain the background behind this test. Basically, here we're slightly moving away from the part which is related to Parkinson disease. Here's basically cognitive abilities and how we learn. what you demonstrated that you are educated person, because we got a data set from a country where you have people who illiterate. They did not attend the school. So basically for them, or they attended just 1 or 2 or 3 classes at school. So many of them could not write. And what happens is that they use a strategy completely different from educated people. So their strategy would be, I will take another color, their strategy would be to do something like this. They could not usually correctly plot the corners, and then what they were trying to do, they were trying to complete this image. So in many cases what you get here, you get not a properly drawn honeycombs, but you get something very, very different. In many cases it can be just ellipses, arbitrary. Another, by the way, another strategy which is used by educated people is to plot this line and then plot these elements independently. This is what we observe. So why we do this research? So obviously this is not to offend anybody, but it's very important in the early years of school educations to capture any deviations from a normal cognitive progress and take an action. So this is one test. It's much more challenging to analyze because here you have quite a lot of freedom due to the fact that you can basically plot whatever you wish. And the second test here is very interesting because here you do not have freedom. You have your reference point, but where you position the cube, where you start to plot it, and in which order you plot diagonal and vertical elements is very important. So what our initial research has demonstrated that there are common 3 element sequences which are very characteristic to different levels of education: uneducated, 3 years of education, fully educated, let's say school education, and higher education level. So this is what we managed to find out so far. Yes?
I have a microphone, I can ask. So in the early phases it was like 2-dimensional image, but clearly in here you need to record the time, which line you draw at what order. So it's not only the final image, but you really want to have the time as it was made.
Absolutely.
And have you been then visualizing them somehow, that the order of the time, or can you put that?
Well, I do not have clear image with me, but yes, we usually visualize it in such a way that we use time as a third dimension, and then we usually visualize it this way. So this is research in progress. We basically publish our first conference paper, and in a shameless act of self-promotion, I can say we got a second best paper award for this conference. This is one of the directions we work very intensively now, because again we got a positive feedback post from computer scientists, let's say, and from this cognitive research, psychology research. So, and here, yes, you have order, or how you combine these, let's call primitive elements of the drawing. This is one topic of ongoing research, and here, as you can see, we jumped from purely medical part, we jump more to kind of education or cognitive science part. Well, I know that my time is soon will run out, and I should leave some time for questions, but the last thing, I would like to return to the beginning. I would like to return to spiral drawing test, And I would like to return to the question of explainability, because this is important. And first, we were very happy with what we received. We thought we have a spiral drawing test, we have our CNN model which is sufficiently accurate, and now we find a very good explainers to put in and get finally full workflow which will explain the part, or will also highlight the part of spiral which was most important in making the decision. And when we observed numerous examples, unfortunately our first moment of happiness disappeared. And why it's disappeared, you can take a look into the last diagram here. So why machine made a decision, or why explainer thinks that machine made a decision observing something which is not even an image. So it's like one of my colleagues, he liked to joke about it. He said, yes, and this is small snowman in the corner of an image which allowed us to distinguish between wolf and a husky. So this is a problem, but actually you can ignore some images, let's say that they're faulty, and for example you can concentrate on the first image and everything looks bright here. What we have here, we have a beautiful diagram, and in majority of cases we say that okay, Parkinson disease patient could not stop properly the motion, it's complicated for them, and this is what you have here. But then you have another explainer run on the same exercises, and another explainer for the same model shows completely different parts. So first I was trying to interpret this using very simple logic. I would say that you would like to buy a car, and you would like to buy definitely a red car. You go to the car shop, but they did not have a red car, and there was a car without an engine, and you did not bought it, and explainer will definitely highlight only the most important components. There is no point to even consider the car without an engine. But then basically here we need to get more input from our medical colleagues, because usually diagnosis is stated not just on the basis of one symptom, but you should have quite many of them. Well, and this is another very active part of research for us, because we would like, and we really would like to have this very good XI component, but something still requires polishing and requires quite a lot of attention here. But and on this positive note that work will go on, and we still will work on it, I would like to conclude my presentation now, and maybe we should turn to questions and discussion.